Hi, I'm Nirja Joshi, and this is my CS 5100 Foundations of AI Capstone project. For this project, I reproduced a 1997 paper by Keno and colleagues titled Solving Constraint Satisfaction Problems by a Genetic Algorithm Adopting Viral Infection, published in Engineering Applications of Artificial Intelligence. Now, let me start with the problem. A constraint satisfaction problem, or a CSP, is any task where you have to assign values to a set of variables such that a bunch of rules between them are all satisfied simultaneously. You can think of Sudoku, timetabling, map coloring, or register allocation in compilers. All are CSPs. These problems are NP complete in general, so for anything reasonably sized, we rely on heuristic methods rather than the exact ones. The paper I reproduced proposes an unusual twist on genetic algorithms for solving the CSPs. Instead of using the random mutation to explore the search space, it introduces an operator called viral infection. The idea is that small fragments of partial solutions, called the viruses, get injected into candidate solutions. Now, these fragments that improve the fitness get promoted, and the fragments that hurt the fitness get demoted. The authors claim this makes the search faster and more reliable, especially on the low density problems. Now, let me quickly walk through the key concepts from the paper. A CSP is defined as a four tuple U, L, T, and R, as you can see here. U is the set of variables, L is the finite domain of the values each variable can take, where T is the set of constraint scopes, which are the pair of variables that constrain each other, and R is the set of allowed values pairs for each constraint. And a solution is an assignment that satisfies every constraint in the R. Now, two quantities characterize the difficulty. The constraint density, D, it is the number of constraints divided by the number of variables. And R mean, it is the average size of each allowed value pair set. Smaller R mean means tighter constraints. Counterintuitively, low density problems are harder for local search because the cost landscape has many isolated local optima. Now, the main innovation GAVI, that stands for genetic algorithm using viral infection, keeps the standard GA skeleton, population, roulette selection, uniform crossover, but removes the mutation. In its place, a separate virus population is created where each virus is a constraint scope paired with one of its allowed value pairs. Now, during the infection, viruses are sampled by infectivity and they override the two loci they name on a chosen individual. If the fitness rises, the virus infectivity rises. If not, it drops. Good partial solutions, therefore, spread through the population in a directed way. The paper's central claim is that this GAVI algorithm should be faster than a standard genetic algorithm on low density CSPs and more robust than iterated hill climbing. Now let me walk through my implementation. The whole thing is in a single Python file and no external libraries, just the standard libraries used. At the top, I have a CSP class that stores the four tuple N, L, T, and R plus a hidden ground truth solution. Now, these properties Give me M, that is the density, and R mean whenever demanded. Now, here is the random CSP generator. Given N, target M, domain size, and targeted R mean, it does three things. First, it samples a random hidden solution. Second, it samples the M variable pairs without replacement as constraint scopes. And third, for each constraint, it draws a set size near R mean and populates the allowed pairs. Crucially, the hidden solutions induced pair is always included. So every generated CSP is guaranteed satisfiable. This is important because otherwise success rates would be would be polluted by instances with no solutions at all. These are some different functions that I've defined. Fitness is solution or not, argument max, least mean, the rowlet selection that is based on the probability. Here comes the IHC, that is iterated hill climbing algorithm. These all are the shared utilities. Now, here is the IHC baseline, that is iterated hill climbing. It uses the mean conflicts heuristic. Pick a conflicting variable, try every value, and keep the best. If it stalls, restart from the scratch and matches the G-side paper style baseline in the paper. The next algorithm is the genetic algorithm. This is the standard GA, population of 500, uniform crossover, 2% local mutation, roulette on squared fitness with elitism. The third and the last algorithm is the GAVI, which is, you can say that it is actually the star of the show. At the top, I have built the virus pool directly from the problems R, that every constraint scope paired with each of its allowed value pairs. Each virus starts with infectivity 1. Inside the generation loop after crossover, I pick a fraction of offspring equal to the infection rate. 40% in my runs, and for each I have a sample virus proportional to its infectivity that overrides the two loci, recomputes the fitness, and updates the infectivity by plus or minus zero point 0.1 depending on whether the fitness improved or not. Now, fitness guided infection is doing the directed work that mutation was doing in the GA, just match better. Now comes the main block. Down at the bottom, run experiments is there, which runs all the three solvers on the same instances and returns the aggregated success rate and mean time. The main block sweeps over 5 densities, 3 mean values, and 3 instances, that is for 10, 30, and 50 CSPs. These are the densities 0.98, 2, 3, 4, and 5, and it runs for 3 R means, that is 2, 4, and 6. Actually, the genetic algorithms take quite a few time to run. So I've already ran this code before and I have my results here. So, so I ran the full experiment 3 times. One with 10 CSPs per cell, once with 30 CSPs per cell, and once with 50, so that I could check that how stable the estimates are as the sample size grows. So let me walk through each. Starting with the 10 CSPs per cell, even at the small sample size, the pattern is already visible. At R mean equals to 2, Gavi scores 100% of the instances across the all 5 densities. While the GA drops to 70 to 80 in the middle range, at R mean equals to 4, the GA collapses at 10%, at D equals to 3, 30% at D equals to 2 and 4, the Gavi holds 100% everywhere still. And so the qualitative story is clean even with just 10 instances, but the numbers are noisy. For example, the IHC's success at R equals to R mean equal to 4, the D equals to 9.0.98 is 30% here, which is one of those noisy cells. Now 30 CSPs per cell. So the numbers tighten up. At R mean equal to 2, the GA picks itself up a little, ranging from 66 to 100 across densities, but Gavi still holds at 100% everywhere, with mean times between 1.3 to 2.5 seconds. At R mean equals to 4, the GA stays collapsed in the middle, while Gavi is still at 100% across the board. At R mean equals to 6, the GA is again at 0% for D equals to 3, as you can see here, and also for 4, but the IHC is noisy 30% at R mean equals to 4, D equals to 0.98, and from the 10 instance run has now settled to 43%, which is a better estimate, but still shows that iterative hill climbing is failing on this hard cell. So now finally 50 CSPs per cell, which is the main result I reported. The ordering between algorithms does not change, but estimates are now the cleanest. At R means equals to 2, Gavi solves 100% in every cell between 1.7 to 2.7 seconds per run. The GA drops to 62% at D equals to 2, as you can see here, and takes 4.7 to 7.2 seconds when it does succeed. There is a factor of about 2.5 to 3 times speed up for Gavi, consistent across every density. Also at R mean equals to 6, which is the toughest regime, look at the GA row. It is 52%, 2%, 0%, 0%, 0%. The GA is essentially useless here, but the iterative hill climbing is 52% at D equals to 0.98, 68% at D equals to 2, but the Gavi is 98%, 94%, 100%, 100%, and 100%. It is the only solver that functions across the whole grid. So to wrap up, I classify this paper as partially reproducible. The core algorithm is described clearly enough that I could build a working implementation from the paper alone, and the two headline claims hold up strongly in my runs. But the random CSP generator and the exact form of the infectivity update and the statistics used for reporting are all underspecified. So I can't cover the paper's exact numbers, only the correct trend and the correct ordering of the algorithms. The full code report and the experimental logs are in the GitHub repository linked in my report. Thanks for watching.